Welcome. All right, let's get into it. Our exam is on Tuesday, and I've talked extensively about that already. So any questions about the exam as you've been thinking about that coming up? Yes? Excuse me? Yes, the equation sheet. In what way?
The way the equations are written, they're all mixed up together.
That's not true. They're in chronological order, like how we've taken them through the semester, with one exception. That's at the last. So, I mean, you don't have to use the equation sheet. It's not required. If you'd rather commit the equations to memory, that's fine. No, you may not. You can only use the equation sheet that I provide. Yeah. Any other questions about the exam? All right. So today we're going to continue talking about stability of floating bodies. And essentially what this is all about is why boats don't tip over. If you've wondered that before, looking at how tall boats sometimes are. And we talked about some of the fundamentals when we were in class on Tuesday. And just to remind you, G is the center of gravity and C is the center of buoyancy. And so the center of buoyancy depends only on what's underneath the waterline. So you can think of it as the center of area underneath the waterline. The center of gravity, on the other hand, includes not only what's under the waterline, but also the things that are above the waterline. And it's not based on the area. It's based on where the mass is. And so if you have a very heavy mass at the top of the boat, that would move the center of gravity up more than if the heavy mass is in the middle of the boat. One of the things you have to know is that gravity acts down and buoyancy acts up. I think you've probably already seen that on plenty of occasions, including the homework assignment you just submitted. Now, if you tip the ship over, it's going to change the shape of what's underneath the waterline. And this curved shape on the boat is partly to make it so that there's less drag as the ship moves through the water. But it's also because when the boat tips over, what we want it to do, if it tips over temporarily, is we want it to come back up again. We don't want it to continue tipping or to go in circles like that log was, which was neutrally stable. But what you'll notice about now that we've tipped it to the side, the center of gravity is in the same place, because by tipping the boat, that doesn't necessarily shift the load. Although if the load isn't ratcheted down, it can move around on the deck. But let's assume that everything in the ship is securely held, and so that the center of gravity stays in the same place. But what you'll notice is that the center of buoyancy is shifted to the right, because look at what's now underneath the waterline. The shape of what's underneath the waterline, the center of area has moved to the right. And so because of that change in the location of the center of buoyancy, now you have a righting couple, where you have the gravity acting down, the buoyancy acting up, but they're not on top of each other. They're side to side so that it's pushing the boat so it'll tip upright again. So just to point out one thing, this M stands for metacenter. And the metacenter is the location that the center of buoyancy will always point to. And so if we tipped the ship over even more, maybe it makes the center of buoyancy over here. But the location that it would be pointing to, it would be pointing towards the M. So it's kind of a central point. In the same way that if you draw a curve like this, if you draw a quarter circle, there is a point at which we could measure the radius. And so that location has kind of an analogy to what we're saying here with the metacenter. The metacenter is a point that the center of buoyancy is always pointing towards. Now, even though the center of gravity is above the center of buoyancy, that's what makes this stable. I mean, the best case scenario is that your center of gravity is beneath the center of buoyancy. And let me go back to the earlier example we were looking at in the previous class. In the previous class, we had this drawing. And here, it was stable because the center of gravity is below the center of buoyancy. And so this is very stable. But what we're saying is that you can even have the center of gravity above the center of buoyancy, like we have with this ship, because the shape is changing as it tips, the shape of what's underneath the waterline. A circle, as it rotates, as the circle tips, its shape isn't adjusted. What's underneath the waterline isn't changing. But here, this boat has the fact that the center of buoyancy is going to shift to the side. So what we can deduce is that if the metacenter is above the center of gravity, then the object is stable. So what you have to do is you have to find out if M is above G, because that's going to be our new criteria for what makes a boat stable. If M is below G, then the ship will tip over. If it gets hit by a wave, or if it starts to turn, anything that would cause the ship to begin tipping, then it would continue to tip until it was completely over on its side. So remember this criteria. If M is above G, then the object is stable. So if G is above M, then it's unstable. One of the things we're going to need to remember when we measure and calculate the distance between the metacenter and the center of gravity is the area moment of inertia about the waterline. Let me bring the lights down just a little bit so you can see this image better. This is a barge, and you'll remember our area moment of inertia formula, AB cubed divided by 12. When we were doing this for vertical situations like plates that are under the water, what did we say was A and what did we decide was B? If we had, for example, here's the water and here's a plate that's under the water, what was A and what was B? B is the vertically oriented one, because you could sort of say B is more important. You know, the depth parameter is more important. When we're talking about hydrostatics, you know, it's the depth parameter that deals with the pressure. And so when we had a vertically oriented plate like this, we would cube B, which being the vertical component. Now here, you can see that one of those is longer and one is shorter. In the case of almost every boat, very few boats are going to be square-shaped. And so the parameter that we cube is the shorter one. It's sort of the critical thing. If this boat was going to tip over, think about it. If it was out in the bay and some waves started hitting, what's the most likely direction it's going to tip? Is it going to tip end over end the long way? No. It would tip side to side. And so we need to cube the critical dimension, which is the shorter of the two lengths. So that's how we're going to do the area moment of inertia. And even if it's a ship that's not rectangular, it can be somewhat approximated as a rectangular shape. So there's this parameter called metacentric height, GM. And remember, GM is the distance between the center of gravity and the metacenter. And so those things they're not labeled on the ship. You know, there's not someone who's assigned to go out and paint it on the side of the ship. It's not something you can just take a tape measure and actually physically measure. What we do instead is we calculate it based on these things. First of all, I, the area moment of inertia, which we've just talked about on the previous slide. V is the volume that's submerged underneath the waterline. So for a ship like that, there's usually on the side of ships, it actually does have markings corresponding to how deeply submerged it is in the water and the weight that the ship is carrying. In our case, we're going to do an example today where you'll calculate the submerged volume based on some dimensions from a drawing. Okay, so that's I and V. And then CG is just the distance between the center of gravity and the center of buoyancy. So again, the center of gravity depends on where the load is on the ship. So a container ship that has many, many stacks of those metal containers, it could possibly have the center of gravity very high, even above the waterline. And then the center of buoyancy for the square-shaped container that we're going to be dealing with today, the center of buoyancy is just halfway down from the waterline to the bottom edge of the object underneath the water. So our criteria here is if this quantity, GM, is positive, then it'll tip temporarily, then it'll come back into stability. So GM positive means the body is stable, but if it's negative, what that tells you is that the center of gravity is above the metacenter and it would tip over. This is the criteria. Here's the formula. And let's see. I seem to remember there was one more thing I was going to tell you about. We'll get to it. Oh, okay. Yeah, here it is. All right. So how can we make a ship more stable? If you look at this formula, a positive GM means that it's stable. A negative GM means it's unstable. And so stability is when this first term is big, and instability means the second term is large. So let's think about loading the ship. If you're putting things onto the ship to take it on a voyage, one of the things that would make it unstable is if you have the center of gravity really high in the ship. And so if you were loading steel ore and cotton bales into a ship, and you put the cotton bales at the bottom and the steel ore at the top of the ship, then that would move the center of gravity upwards in the ship. And so what would make it more stable is you put the heaviest load at the bottom to try and bring the center of gravity low in the ship. Now what about this first term, things that will make a ship more stable? Any ideas? What about the volume? Yeah, we want a small volume because since V is in the denominator, we want this term to be as big as possible. So we want a big I and a small v, right? So the things that can make a big I is a wide ship. A narrow ship would mean it's going to tip over more easily. So let's play around with that. And here is the example. Now I've printed out a paper for you. What I mentioned in my email is that you're going to submit this and it counts as homework points. I'll just record the score up in my office, and so it's worth 24 points, and you're allowed to work with your classmates on this one. But I've changed the order around. The things that I'm asking I have written on here A through H. The parameters are still the same. It's still that the load is 181,000 kilograms. It's 6 meters wide. The barge is 2.44 meters from the top to the bottom. You can see where the center of gravity is. So here on the page, I'd like you to go through A through H and label each one of your responses. And we're going to have the remainder of our class time to finish that. This subject? Yeah.